So next speaker is Chiheng Dong from China. He will present online. Are you there? Chiheng, do you hear me?
Yeah, I'm here. Okay.
Okay.
Can you see me?
You can share and start, please.
So you
can
see
you. And it is clear. You can start.
Okay. Hello, everyone. Thank you for inviting me to this great conference and give a talk on our recent advances in iron-based mounting wires and tapes and their applications. And here is our collaborators, and thanks for their contributions in IC measurements, the coil fabrications, frost pinning, and reboundary characterizations. And my talk includes 4 parts. And let me first give a short introduction to iron-based PIT wires and tapes. So in the future, the high-field magnets used in next generation accelerators and tokamak require high-performance mounting wires. And for now, there are several commercial mounting wire tapes, such as niobium titanium, niobium 13, bismuth 2212, 223, and YBCO. So which one is the best candidate actually depends on their characteristics. For example, the intrinsic properties such as anisotropy, the critical current density, the upcritical field, and the chemical stability actually depends on the thermometers itself. But there are some other extrinsic properties such as assay loss, thermal stability, and mechanical strength actually depends on the conductor design. Moreover, the fabrication process must be scalable to fabricate long wires and tapes. And the last but not the least is their cost. The price must be lowered down to lower down the cost. So in 2008, Professor Hosono discovered iron-based semiconductors, and it has a very high TC, very high upcritical field, and a small anisotropy, and they have very high critical current density, making them very promising to be used below 30 Kelvin and in the field above 10 Tesla. However, iron-based semiconductors are ceramics, so it's very hard to directly fabricate into long wires. So we use a powder-in-tube method to fabricate long wires and tapes, and here is their fabrication procedures. And after decades of investigation, we found that the barium potassium 1-2 system combined with silver or silver alloys are very good to achieve a high GC. Another advantage of IBS is their low material cost. On the one hand, iron-based semiconductors includes elements that are have richer abundance than the cuprates. And on the other hand, because there is no need for annealing in oxygen, so we can directly combine stronger outer sheets such as copper, alloy in the outside, and silver only acts as a block layer. So the cost of IBS wire and tapes can be 4 to 5 times lower than that of niobium 13. And due to the very good performance of iron-based semiconductors, Chinese government have invested about $56 million to increase the critical current density of iron-based semiconductors, and of course, very good Arabico and bismuth 2212, and decrease their cost to $3 per kilo ampere meter. And the best one will be used in the next generation accelerators, which will SPPC, which will maybe developed in China. So this is a great opportunity for the development of iron-based melting wire tapes. And of course, it's a very long way full of challenges. Then I will talk about the 3 rules to achieve a high GC, including the grain conductivity, grain texture, and grain boundaries. As we know, there are 2 important factors that affecting the GC of iron-based melting wires and tapes. The first one is the grain misorientation. And when the misorientation angle between the adjacent grains is larger than 9 degrees, the intergrain current will be largely decreased. So for now, we can achieve a partial C-axis texture in the PIT tapes. The second factor is grain conductivity. And the best circumstance is very closely connected grains with very clean grain boundaries. And the parameter to describe the grain conductivity, we use surrounding core density. So for now, there are 3 ways to increase the core density and texture. The first one is hot isostatic pressing. For example, we use copper-silver architecture, and by using the 150 megapascal pressure, we can achieve a very high core density. The second one is a mechanical deformation, and especially for the flat rolling process to introduce CX texture. And this one can sinter at ambient pressure. And the third one is a hot pressing process, and the pressure is only 30 megapascal, and we can get a very high C-axis texture. So I will firstly talk about the hot isostatic pressing. As you can see here, the cracks and worries are largely decreased in the heap wires and tapes. The core density can increase to 96% of the theoretical value, which is much higher than the load one. And here is our best wires and tapes. At 4.2 Kelvin 10 Tesla, the JC of the round wire is 47,000 ampere per centimeter square. And for the tapes, because of the increased CX texture, the JC at 4.2 Kelvin and 10 Tesla exceeds the level for practical applications. Actually, we can only get poor grain texture in the heap wires as evidenced by the XRD measurements and EBSD measurements. Although the plate-like grains lie along the y-axis, and we can get a homogeneous bar current across the wire plate. On the contrary, the CX texture is largely increased in the heap tapes. And when we, with the increasing reduction ratio, we can simultaneously get an increased C-axis texture and increased plate current density. So the heap process is a scalable and cost-effective fabrication route to produce long wires and tapes. The second one is mechanical deformation. And here is an example. We use a stronger outer sheet stainless steel, and by flat rolling, we can introduce C-axis texture and high core density as well. The vehicle hardness of the surrounding core can be increased to 277, which is very close to the heap wires and tapes. And we have fabricated a 1 meter long tape. It has a very homogeneous JC, and the best JC at 4.2 Kelvin and 10 Tesla is above 80,000 ampere per centimeter square. And this is also a very a scalable way for long wire production. And actually, the best critical current density is fabricated by the hot pressing method. And this is our new data. And at 4.2 Kelvin and 12 Tesla, the critical current is 548 ampere. So this is a very large value, and the GC achieves 35,000 ampere per centimeter square at 33 Tesla. And as you can see here, the voids and the cracks are largely decreased in the hot press tape. However, the vehicle hardness is only a little larger than the flat roll tapes and much smaller than the hip wires and tapes. On the contrary, the CS texture is largely enhanced in the hot press tapes, as evidenced by the EBSD results. There are 38% of the grid boundaries with orientation smaller than 10 degree. However, there is only 12% for the roll tapes. So what is the difference between heap and hot pressing? For the heap process, the pressure is actually isotropic. So there are very little deformation and very little mass flow in the heap wires and tapes. But for the hot press tapes, because there are no limits on the two sides of the tape, so we can see a large deformation in the transverse direction and the mass flow also in the transverse direction, maybe like this. And we can see that in the heap wires and tapes, the grain is more closely connected, but the thickness texture is not enhanced. Actually, in the heap tape, the thickness texture is only introduced by the flat rolling process. But in the hot press tape, because large extension in the transfer direction, we can see that the grains are forced to lie in this direction. So the thickness texture is largely enhanced. Another challenge is grid boundaries, as evidenced by the atom probe tomography or TEM. They found there are large amounts of iron arsenide wetting phase, which actually making the grid boundary into SNS US junction, or even worse when the grid boundary is thicker than the coherence length. So this is a great challenge, but also when we solve this problem, I think the GC will be largely increased to a new level. And then I will talk about the recent applications of iron-based mounting wires and tapes. The first property must be considered is the mechanical properties. The equivalent stress from the magnetic energy is estimated to be 160 megapascal at 20 Tesla. However, silver is very soft. The critical stress is about 35 megapascals, and the reversible tensor strength is only 0.25%. So stronger outer sheaths is necessary in iron-based mounting wires and tapes. Then we perform bending diameter test on our 100 meter long tapes. It's 7 filaments tapes, and we fabricate these special devices to with different binding diameters from 10 millimeter to 30 millimeter. And we test their IC at 4.2 Kelvin and 10 Tesla. And here are the results. The ratio actually is above 80% when the diameter is larger than 15 millimeter, but there is a rapid decrease of IC in the 10 millimeter sample. So what happened? And as you can see here, there are transverse cracks at the start of the bending region and it continues in the arc region. So the transverse cracks largely limits the critical current. And thermal conductivity is also very important, and we measure different composite types and found that the thermal conductivity of iron-based silicon types is actually dominated by the sheath material. We can adjust the thermal conductivity from 1 to 1000 watt per meter Kelvin by adjusting the sheath material. And the copper silver has a very large thermal conductivity and very cheap to apply in the high field magnets. Moreover, we found atom diffusion between different sheaths and supernating cores. That must be careful when we choose sheath materials. Supernating joints are very important for applications, and here we use a cold pressing method to fabricate a very good supernating joint. The critical carbon ratio is increased to 95%. This is a new record. And by using the field decay measurement, we can see that the joint resistance is decreased to 10-13 ohm at cell field and 4.2 Kelvin. It's very good news for the persistent model MRI magnets. And of course, we are continuous fabricating the 100 meter long tapes by using the flat rolling process. And the tapes have a very good homogeneity. And our new data shows that the critical current density at 4.2 Kelvin and 10 Tesla is above 50,000 ampere per centimeter square. And they're a very important step to practical applications. And based on our 100 meter long tapes, we cooperate with Chiheng Dong group to fabricate the world's first pancake coils. And we can get a very good performance at 24 Tesla. And here the inner diameter is actually 30 millimeters, and we continue to decrease the inner diameter below 20 millimeter to fabricate the single double pancake coils and the 6 double pancake coils and test them in the water-cooled magnets at high fields. Now here is the results. For the single double pancake coils, we get 67 ampere at 30 Tesla. This is a new record. And for the 6 double pancake coils, we can get 124 ampere at 4.2 Kelvin and 10 Tesla, which is about 69% of the short sample. And here we use 100 meter long tapes to fabricate the world's first racetrack coils. By using the metal as insulation technique and the wind and react at above 800 degree, then we can get 65 ampere at 4.2 Kelvin and 10 Tesla, which is about 87% of the short sample. This is a very great news. And all these results indicate that iron-based supernating long wires and tapes are very promising for high field magnets. And here is my conclusions. And iron-based supernating wire and tapes are quite promising to be used in high field magnets. And we can now achieve JSA above the practical application level in short samples. And the 100 meter long tapes have been fabricated and already used in supernating coils, and of course for demonstration. And the next step to high GC, in my opinion, we must maybe get a better CS texture and of course more clean gray boundaries. And our next target is 100,000 ampere per centimeter square at 30 Tesla. Thank you for your attention, and welcome to our lab to pay a visit. Thank you.
Thank you for your nice talk. Are there any questions? Please.
Okay, thank you very much for showing us this interesting results. I have a question concerning the 100-meter tapes, because as I understand, these are flat rolled. And my question is, because you showed that the best would be hot pressed, because the texture is the best. Do you have plans or any attempts on making a long length hot pressed or like hot rolled tapes, something like that?
Oh, actually, the hot pressing method is can be only applied in short samples because the device is limited about maybe 10 centimeters. So for the long wires, we can only use a flat rolling process.
Plans to get that into longer lengths?
Yeah, flat rolling is actually what we are using now. But in our next step, maybe we can use hot isostatic pressing to increase the core density.
Okay, thank you very much.
Are there any questions? So you don't have questions from the online also. Thank you very much again.
Thank you, everyone. Thank you, everyone.
Okay, we have a coffee break here for 10 minutes.